Take a sugar cube. Now imagine it weighing as much as every single human being on Earth combined. That is not a thought experiment. It is a confirmed, documented property of neutron stars, published by the European Space Agency. These objects exist right now, in our galaxy, doing things no law of physics on Earth can fully explain yet. I was going through a NASA Goddard simulation published in November 2025. Two neutron stars spiraling into each other at nearly the speed of light, and I had to stop and just sit with it. The energy released was described as the most powerful explosion in the known universe, and we have now detected the gravitational waves from events like this arriving at Earth. We felt the ripple from a collision that happened before our civilization existed. What the headlines are not telling you, neutron star research in 2025 and 2026 has completely rewritten what scientists thought they knew. A sleeping neutron star roared back to life in December 2025, observed by astronomers at Eheim University. NASA's Roman Space Telescope, launching September 2026, is designed to reveal millions of neutron stars currently invisible to us. The real documented science of what these objects are, and what the latest discoveries reveal, that is what we break down today. A neutron star is what remains after a massive star, between 10 and 25 times the mass of our Sun, reaches the end of its life and explodes in a supernova. The outer layers are blasted away, and the core collapses under gravity into something almost unimaginably dense. What is left behind is a sphere roughly 20 kilometers across, about the size of a city, but containing more mass than our entire Sun. A sugar cube-sized piece of neutron star material would weigh as much as every human being on Earth combined. The matter inside is compressed so tightly that protons and electrons are forced together to form neutrons, packed almost as densely as an atomic nucleus, but stretched across a sphere kilometers wide. Nothing on Earth comes close to this state of matter. The surface gravity of a neutron star is approximately 200 billion times stronger than Earth's gravity. If you dropped an object from 1 meter above the surface, it would hit the ground at around 7 million kilometers per hour, accelerated in a fraction of a second. Nothing that lands on a neutron star's surface survives in any form. The gravitational compression would flatten any known material into a layer thinner than an atom. The escape velocity from the surface is roughly half the speed of light, meaning even to leave the surface, you would need to travel at 150,000 kilometers per second. This extreme gravity also warps space and time around the neutron star in ways that are measurable. Light itself bends visibly as it passes near the surface, an effect confirmed through observations and consistent with general relativity. Some neutron stars rotate at extraordinary speed while emitting beams of radio waves from their magnetic poles. If those beams sweep past Earth as the star rotates, we detect regular pulses of radiation, like a cosmic lighthouse. These are called pulsars. When astronomers first detected these perfectly regular pulses in 1967, the signals were so precise that they briefly considered whether they might be artificial. They were later confirmed as rotating neutron stars, yet their precision rivals atomic clocks. The fastest known pulsars spin hundreds of times per second. The record holder rotates 716 times every second, a city-sized object, more massive than the Sun, spinning at that speed without tearing itself apart. A subset of neutron stars has magnetic fields so intense they form a separate category entirely, magnetars. Their magnetic fields reach around 100,000 million Tesla, vastly stronger than Earth's. A magnetar's field is so powerful it could erase all magnetic storage devices on Earth from halfway to the Moon. In 2004, a flare from one even compressed Earth's magnetic field from across the galaxy. The crust of a magnetar can crack under its own magnetic stress, creating starquakes that release bursts of X-rays and gamma rays detectable across space. In December 2025, astronomers documented a neutron star that suddenly reawakened, unleashing a powerful X-ray surge after a quiet phase. As its X-ray output changed dramatically, its rotation rate shifted at the same time, revealing new insights into how matter behaves around neutron stars. These rare events provide critical data because quiet neutron stars are nearly impossible to observe. Each reawakening offers a brief, invaluable window into their physics. When two neutron stars orbit each other, they gradually spiral inward, losing energy through gravitational waves until they collide. These collisions produce gamma-ray bursts, among the most powerful explosions in the universe, releasing more energy in seconds than our sun will in its entire lifetime. They are also responsible for creating heavy elements like gold, platinum, and uranium, meaning much of the gold on Earth was formed in such collisions. These mergers send ripples through space itself, gravitational waves that have now been directly detected on Earth. The first confirmed detection showed that neutron star collisions produce both gravitational waves and light simultaneously, confirming long-standing predictions. This allows scientists to study these events using both signals together, a method known as multi-messenger astronomy. The interior of a neutron star remains one of the biggest unsolved problems in physics. The density is so extreme that current models cannot fully describe it. While the outer layers form a solid crust, deeper regions may contain exotic states of matter, possibly even free quarks never observed directly. This uncertainty marks the edge of current scientific understanding, with future observatories aiming to probe deeper. Every pulsar gradually slows down over time as it emits energy into space, a process measured with incredible precision. Some pulsars experience sudden jumps in speed called glitches, likely caused by internal structural shifts within the star. These glitches provide rare insight into the internal structure of neutron stars, something we cannot observe directly. There may be tens to hundreds of millions of neutron stars in our galaxy, but only a small fraction have been detected. Future telescopes may reveal millions more, helping map their distribution and properties across the Milky Way. This could help answer one of astrophysics' biggest questions, where neutron stars end and black holes begin. In 2025, a planet with a carbon atmosphere was discovered orbiting a pulsar, challenging existing theories. This raises new questions about how planets can form or survive in such extreme environments. It expands what we thought was possible, opening a new area of research in neutron star systems. Neutron stars are not just extreme objects. They are natural laboratories for physics beyond what we can recreate on Earth. Each observation adds a piece to a much larger puzzle that scientists are still assembling. Future missions will continue revealing new discoveries, pushing the boundaries of what we know about the universe.